Okay, sir. I'll make this Zoom session as live in YouTube also.
Mhm.
Okay, sir.
Have you pasted the questions? Sure. Please go ahead.
Sir, are you able to read the questions?
Yes, I can. Yes.
Okay, sir.
Yeah, I'm just getting an echo from the YouTube feed as well. So let me see if I can mute that. Hmm. Yeah. Okay, I can answer these questions. So when we start, do we start? It's the hello.
Yes, sir.
Yeah. Can I start answering these questions?
Yes,
Are
sir.
we
This
live?
all question asked by Sandeep.
Yes, yes,
He's
I
a
can.
student. I think same Sandeep has been joined this Zoom session, I hope. Sir, am I audible?
Yes.
Okay, sir. This all question asked by a single student only.
Oh, I see.
His name is Sandeep. I hope he's the one who joined here. Let's see, sir.
Hello, good afternoon, sir. Myself, Sandeep.
Hello, Mr. Sandeep. Uh, so you're the person who asked the questions in discussion forum, right?
Yes, sir. Yes, yes.
Okay, okay. Yeah, professor is here. Yeah, you can clarify your doubts with him.
Okay. Thank you, sir. In one of the assignment questions, I saw mention about parasitic BJT effect in MOSFETs. Could you please clear that because I couldn't grasp that concept from the lectures.
Okay. Yeah. So can we go through all your questions, Sandeep? We'll start from question 1.
Okay, sir, sure.
Yeah. So yeah. Yeah. Can you hear me clearly?
Yes, sir, we can hear you and see you also. It's clear.
Okay. The first question is, why do we make the source and drain N plus highly doped? And the second question is actually connected to the very first one, which is why do we create N wells? So let me just answer that very briefly. Yeah, I have muted my YouTube feed because it is giving me an echo. It's repeating everything I said a few minutes back. Sandeep, can you still hear me? Can you?
Yes, sir, I have joined through Zoom. I can hear you.
Yeah, okay, fine, perfect. Okay, I'll just work through Zoom, okay? So the first two questions are sort of linked. Why do we dope this N-type, strongly N-type? Okay, and it's got to do with the, if you remember your metal semiconductor junctions, if you remember a Schottky junction, now because of surface states or the interface of a semiconductor and metal, you will end up with a barrier-like contact. Okay, so just try to imagine a Schottky junction where I don't know if there is a whiteboard here. Just yeah, here we go. Um, can you see my whiteboard here?
Yes, sir.
Okay, so imagine a barrier of this kind, right? So essentially, you're not going to be able to get carriers across. I mean, there are mechanisms. There is, just in the case of metal semiconductor junctions, we talked about different mechanisms of charge transport, like uh, diffusion, thermionic emission, and so on and so forth. But still, it's not very strong, like how you would want it to be. So what is done is, and this is not true only for MOSFETs, generally true for all devices needing a metal contact. What is done is you dope this region very strongly. Okay, so let us say this is N-doped, and the donor dopant concentration, you increase it pretty strongly. And by doing that, this band bending will become very sharp. Okay, so let me sort of exaggerate this. So this band bending will become extremely sharp. And why will it become sharp? Because if you write Poisson's equation, right? So if you have, okay, it's terrible with the mouse and okay, if you look at the right side term of the Poisson's equation, it is proportional to the dopant concentration. So by increasing ND, that is making this highly strongly doped, or you want to make it p-doped, increase Na, right? Either way, you make this junction, this band bending extremely sharp. And by doing that, you allow for the tunneling of carriers. So these carriers can actually tunnel through this very narrow region. And therefore, you increase the probability of finding carriers on this site. So that's essentially why we dope any points where there's a metal contact. So you also have tunneling assisting the charge transport, and you will have very strong currents. Okay, so that's brief. That's why you want to improve your metal semiconductor contact, and that's why you have very strong doping at these edges. So let me then go to the third question. Is that clear to you, by the way?
Yes, sir. So we make the width of the barrier smaller so that
Exactly.
electrons can easily tunnel over.
Exactly. Okay, because if you remember, your wave function, it decays exponentially. So with the width of the barrier. So by making this width very small, you basically increase the probability of finding electrons onto the other side. Okay, so let me come to question 3. Consider a case where we apply a VDS much smaller than VGS minus VT. Okay. Also consider VGS above VT such that we have inversion layer. But how does the electron move or accelerate from the source to the drain without having any electric field? No, there is an electric field. So if you have not made VDS 0, if your VDS is not 0, then technically you have an electric field. It is a weak electric field, okay, because your VDS is very small, but nevertheless, there is an electric field. So if you want to imagine the interface of the MOSFET, right, the front end of the MOSFET, you can sort of imagine a region like this. So try to imagine a landscape, okay. You are sitting, you are the gate, and then between you and the screen is the insulator, let's say. And so the insulator semiconductor interface is on your computer screen. So I'm going to draw a landscape for you. So if you go from the source, let's say this is the source, and then you have the drain on the other side. Now, when there is no field, the energy levels are the same. But the moment you apply a certain drain voltage, you have lowered this a little bit. Okay. You lowered this a little bit. Sorry, I'll use the. You have lowered this level a little bit. So going from left to right, you have a landscape that looks like this. Okay, imagine a garden space or whatever, however you like to imagine. And the moment you apply a gate, which means you are the gate, and this region between you and the computer screen is the insulator, and then the computer screen is the semiconductor insulator interface. Now I'm going to draw, I want you to imagine this going into the computer screen, right? So this, you will have band bending like this. So imagine a 3D view, which I'm trying to best represent through my artistic efforts. So you have band bending like this. Okay, can you sort of imagine this? And let's say you have a flat region here, and you have a flat region there, and then you have band bending like this. This is the semiconductor. Does this help you visualize? Is this clear? It's all bending towards you. Okay, it's bending towards you like this. And because of the source drain electric field, you have a slant in this direction. And all the bands, the band bending is towards. Okay, and near your end, that is towards you, you have this, it's coming down. Okay. And as you move away, the bands flatten off. Okay, so this is the region where the band is all flat, right? So you can sort of, so as you head deeper into the semiconductor, the bands are all flat. So now imagine.
But my question is that since we have depletion regions on either ends, at the source bulk interface and at the drain bulk interface, shouldn't the electric field, shouldn't the entirety of the electric field be dropping
not
only
entirety, not
at the
entirety.
depletion regions?
Not entirety. Okay, yeah, it's sort of right, but here on the drain side,
Okay,
yes.
That's why I was confused. I thought that there would be no electric field in the channel.
No. It's not the case. So if you look at the PN junction, so this is the region which will be the depletion region. This is how these two ends will merge into the source drain. So if you look at the source drain like this, source drain, and let's say this is all heavily N-doped, right? Let's say you're talking about a N-channel MOSFET. And if you look at the band bending here, at equilibrium, you have a PN junction of this kind. Okay, this is your depletion region. These are your depletion regions at equilibrium. The moment you make, you only apply a drain voltage. There is no gate voltage applied yet. You only apply a drain voltage. Then you will end up with something similar but this is now bent a lot. And now when you apply a gate voltage, you have the gate field influencing this band bending, and you will end up with the bands becoming a little shallower like this. And because you made it a little shallower, you have strong diffusion of electrons from there to here. Okay, so it is like a PN junction and forward bias. Yes, there is a drop across the depletion region, but it doesn't mean there are no carriers, and it doesn't mean that there is no electric field in the channel region, because there is a source drain electric field seen for you in the channel region. Near the drain side, yes, this region has got a huge voltage drop. In fact, it has got a voltage drop. If your VDS is going to continue increasing, then it will have a voltage drop of VDS minus VGS minus VT, because this point, if for example, if the MOSFET is in saturation, this point will become the pinch-off point, and the rest of the region will have VDS minus VGS minus VT as the voltage drop. But you will have a very strong field also in this region. Okay, so yes, in that case, the depletion region will hold a strong electric field across it, a large voltage across it. But it does not mean that the channel region does not have any voltage drop. The channel region does have drift current, and that voltage drop is caused because of your source drain voltage, right? So there is a voltage drop across the channel region. Okay.
Okay, sir. So there's a finite electric field within the channel, and majority of it drops in
On the
the
drain side, yeah.
drain bulk depletion region. Yeah. Okay, sir.
Particularly when you're above, when you're in saturation mode. Okay, so in fact, that is why you have
Yes, sir.
saturation.
When we increase
So,
VD.
so that in fact, that is why you have saturation. So if you want to imagine in saturation mode, you have this region being depleted. Think of okay, let me put it this way. Okay, so I hope all this discussion is beneficial to all students. So you have source drain. So let's sort of imagine why saturation, or why the current saturates as well, right? So you have source drain, and now you have made VDS greater than VGS minus VT. Okay, so let us say this is greater than VGS minus VT. So if you imagine a MOS capacitor, okay, so you have insulator here, you have the gate above that, and this is the semiconductor. If you imagine a MOS capacitor, throughout the voltage, so suppose VDS is greater than VGS minus VT, there will be a point. There will be a point in this channel where the voltage is, where the channel potential is exactly VGS minus VT. Okay. And if you take a MOS capacitor in that region, you will see that the effective voltage across this MOS capacitor is 0. So there will be no channel charge. Yeah. And beyond this point is actually the depletion region, where the voltage across the MOS capacitor, that is a gate to channel voltage across the MOS capacitor, is not positive. So when you have a channel here in saturation, the channel will always end, so as to say, quote unquote, end at a point where the channel potential is VGS minus VT. So no matter what your drain voltage is, this field as seen by the channel is always VGS minus VT divided by this length, this region where the MOS capacitors are seeing a positive gate to channel potential, right? So this is the region which is always got a drop of VGS minus VT, no matter what your VDS is. Okay. And therefore, the field is more or less constant. If you assume that this length is not varying too much, if you assume this length is not varying too much, and this voltage is always at VGS minus VT, then the current, the field through it is almost constant all the time, irrespective of VDS. And therefore, the current in this region is almost constant all the time. And by the continuity equation, you will have those carriers is accelerating faster here. And therefore, the current through this entire channel region is constant throughout for all VDS above VGS minus VT. Okay, so that is why you have saturation of current. Now, is this length always constant? It is not always constant, because as you keep increasing VDS, the point at which the channel potential hits VGS minus VT is going to be slightly moving in. Okay, it moves in as the square root of the potential, right? Because if you solve the Poisson's equation, it moves as the square root of the potential. So it moves in very gradually. And that's basically a channel length modulation, right? If you take that into account, that the field is slightly increasing because the length is decreasing a bit, that is accounting for channel length modulation. Okay, you've not asked that question, but I'm just putting it out there because it's sort of related. Okay, so is that fine? Could all of you understand?
Yes, sir, it's clear.
This point? Okay, so in a p-doped bulk, we use a metallic bulk contact. P-doped bulk, we use a metallic bulk contact since it acts like an infinite source of so I don't understand this question. So whether it's p-doped or n-doped, you can have a metallic contact, infinite source of electrons. Okay, I think this is what you're referring to. Okay, that's a very oddly framed question, but I think I understand where you're coming from. So let us say you have holes. Okay, I think it's got to do with hole transport in a metal. How do you imagine it? Okay, I think this should clear it for you. I think this is what your question implies. So let's say you have metal and you have an electron channel. So you can easily imagine the electrons in the metal going and forming the electron channel, and the electron channel moves out. Now, suppose you have a hole channel and you have a metal. You still use a metal. There is nothing else. Use the appropriate metal, the work function, etc. set so that it's as ohmic as possible. You have holes, but you can imagine all the electrons in a metal recombining with the holes. Okay, and therefore there is an electron current. All the electrons in the metal are flowing this way, and they're all sort of recombining with the holes at the interface, and therefore you have this continuity of current, continuity of charge. Is that what you're trying to refer to? And is that
Yes,
what
sir.
you mean by, so can you imagine now the current, even though you have a P channel? So
Sir,
it
I was
keeps,
talking about the contact for the bulk. I meant the back contact.
okay.
The phenomenon be the same even for the back contact.
Okay. Oh, you're talking about a bulk contact, is it?
Yes,
Okay,
sir.
what about the bulk contact exactly? Whether some other material is used for the bulk contact, is it?
No, I was wondering for the p-doped bulk, you talked about using a metallic contact for the back contact.
Yeah, for the
Of
n-doped
using a
bulk, you
metal.
dope it appropriately and you use the contact. Yeah.
Okay, sir.
Again.
Then clear,
Yeah.
sir. The question is clear.
Yeah.
The answer is clear.
If I have not answered this, send me an email. I will answer it. Okay. Maybe I'm not fully appreciating that question.
Sure, sir. I'll frame it again.
So what is displacement current? Okay, displacement current is basically your the current through a capacitor, right? So when you sweep VG at a high rate, at whatever rate, okay, you will have a dV by dt value, and that's going to cause a displacement current. Temperature, I mean, yeah, theoretically, yeah, temperature, of course, changes mobility and all that, but otherwise, displacement current is purely because of a dV by dt at where t is the time, in the rate of change of voltage. Why do we always take oxide mobile charges to be positively charged? If there are negative ions, would they shift the CV curve in the opposite direction? Yes, you're right. If it's negatively charged, it will shift the CV curve in the opposite direction. we take it to be positively charged because it's a good example, because typically the mobile charges used to be sodium, potassium. These are some common species that get in. If you have trapped carriers, for example, electrons in the oxide, it is like a negative mobile charge, and you will see the CV curve shift in the opposite direction, right? So the way to imagine it is, first, let's assume that the charge carriers are not mobile, okay? If they are not mobile, but they are there, let's say they are positively charged, it is like as though your transistor has already been, let's say it's an N-type transistor. So it's like as the transistor has already received some gate voltage because there is some positive charge in the oxide. Okay. And you need to apply a little less gate voltage in order to turn on the transistor. So it's like as though you shifted the flat band voltage in a direction where the threshold voltage is going to be lower. It's easier for me to turn on the transistor. Now, if you have mobile charge, one additional complexity is that depending on the gate voltage and the temperature, etc., the mobile charges will move based on the gate field. Now, as they move, the amount they impact the flat band voltage will change. Okay, because if they are closer to the metal semiconductor, the insulator semiconductor interface, it's going to impact it a lot more, as opposed to if it's closer to the insulator gate interface. So you need to take that into account. So that's one additional complexity as to how much it's going to shift. But yes, it will shift in the opposite direction, whether it's negative ions or positive ions. And you can have, but it's more common, practically more common to look at positive mobile ions like sodium, potassium, and so on, and trapped negative charge or trapped holes, which are positive charges.
Okay, sir.
How does shrinking the channel width impact gate control threshold voltage, and how shortening channel lengths impact current in VTH? Okay, so when you shorten channel width and channel length, they have opposite effects on the threshold voltage. So when you shorten channel length, firstly, the gate, let me talk about the gate control. When you shorten channel length, you're bringing the drain closer to the source. And therefore, the drain voltage itself can sort of influence these barriers. And, the presence of a drain voltage itself might turn on the transistor, so as to say. Okay, it can lower the barrier near the source, and the source can start pushing carriers into the channel region. So the gate might actually lose control. But with regards to threshold voltage, because your depletion regions of the PN junctions in a conventional enhancement mode kind of MOSFET, because the depletion regions of the PN junctions is a significantly larger percentage of your channel length, those regions are already depleted. Okay, so for threshold voltage, you can sort of imagine the various steps, right? The milestones, so as to say, for a MOSFET to achieve threshold voltage. The gate voltage to match the threshold voltage. What are these milestones? Firstly, you achieve flat band, which could be a positive number or a negative number, and it's purely dependent on the metal semiconductor work function difference. It's dependent on the trap charges in the oxide and so on. So the flat band voltage is whatever it is. It could be a positive number or a negative number, doesn't matter. You achieve flat band, and then you then have to deplete the interface. So you keep adding charges on the gate, and there is enough charge such that the semiconductor interface is depleted. And then further, you keep adding enough charges on the gate so that you invert the interface, right? You have enough carriers at the interface, and a textbook definition, which need not be the definition you follow. A textbook definition of threshold voltage is that the charge concentration at the interface matches the charge concentration in the bulk. Okay, which will be the majority carrier concentration in the bulk. Now, so that is a threshold voltage. Now, how does reducing the channel length affect this? This second milestone I talked about, which is you have to deplete the semiconductor. The job is almost half done because the source semiconductor and drain semiconductor depletion regions are a significant percentage of the depletion region when it comes to short channel devices. So the threshold voltage appears a little lower. When it comes to channel width, shrinking channel width, two things happen. One is you're shrinking channel width. So the gate, if you look at the cross section, the gate region becomes like a sharp, what do you say? Let's say a needle. Let me use that word. It's like a sharp needle into the semiconductor, right? And firstly, the field spreads out. Okay, the electrostatic lines, the electric field lines spread out. So although the gate region is very sharp, it has to still, what do you say, deplete a larger region as opposed to what is actually covered under the channel. There is a lot more accessory regions that have to be depleted. And therefore, it appears like the threshold voltage increases, okay, when you reduce channel width. Okay. And your next question is also linked to short channel devices, which is parasitic BJT action. Okay. So as you, so there are several things that happen here, right? So if you keep reducing a channel length, your source drain region keep getting closer and closer, which means you're now ending up with a band bending. Firstly, I talked about this drain influencing the channel region. Okay, that is something called as drain-induced barrier lowering. But there are many other things that happen. So as you keep bringing these closer and closer, you're now creating, if you think about the depletion, think about this path, right? You have the n-doped source, you have a depletion region, and then you have a channel, and then you have another depletion region, and then you have an n-doped source. And this channel lies in the semiconductor, which has got a p-type body. So you have an N plus depletion region, a very thin P, another depletion region, another N. So this is like a BJT, okay, BJT-like structure, because the base region is now very thin, and you can actually have current control deep inside the semiconductor away from the gate. Okay, that is a second effect. A third effect is that now imagine your channel length is very small. So you now have electrons from the source running towards the drain during normal transistor operation. Now, as they approach the drain, the electrons have got very high velocities because this typically happens in constant voltage scale, because the fields are much larger because of your smaller channel lengths. So as the electrons approach the drain at high velocities, they might have the energy to knock off electrons from the silicon atoms or your atoms of the, which are sitting in the channel, in the path of the electron. So now you're going to create electron hole pair. It is one of a recombination generation mechanism. Okay, it's called as, it's a generation mechanism. It's called as impact ionization. So you're now creating an electron hole pair. And what will happen to the electron? It's going to follow all the other electrons and run away into the drain. But what's going to happen to this hole? This hole is going to migrate into the body, the semiconductor, which is here a p-type body. It's going to migrate down away from the drain because the band bending is so. It's going to move away from the drain into the p-type body. But the p-type body has got some resistance, right? It's got a resistivity of 1 by PQ times the mobility of the holes. So there is some finite resistance. So as these holes are migrating through the body, there is going to be a voltage drop across this resistor. So the body potential is going to start increasing. Okay. And if this body potential starts increasing, it is like as though you have increased the body source potential. And if you increase the body source potential, what happens? The threshold voltage lowers. And when the threshold voltage lowers, the source is going to inject more carriers. And you end up with this positive feedback effect, which can eventually damage the transistor. Okay, so these are some of the things you need to be worried about when you're talking about short channel devices. What is a transit frequency and why is it also? Okay. Oh, by the way, I'm sorry, I'm just it's a one-way conversation. Are you able to follow all this which I said?
Yes, I could follow it.
Yeah, follow it up. And all the rest of the audience, I hope this conversation is useful. Please interrupt if you need. If you have questions of your own, you can put it in the chat. I'm just looking into the Zoom window here. Yeah. So What is transit frequency? Okay, transit frequency is, so let's say you've got a MOSFET and you've got a time varying voltage that's being applied to the gate. So let's say the gate voltage is some V0 sine omega t. Okay, you've got a small signal AC voltage being applied. So what is that current through the gate? It is C dV by dt, right? And what is my C? Let me write this. Okay, so you have a MOSFET. You have a MOSFET, and here you have V0 sine omega t. Okay, and this is my VGS. Let us see. And this is my small signal VGS. Okay. So what do you mean by small signal? Okay, I've not offered an analog circuits course here on NPTEL, but let's say there is some bias voltage. Okay, you got a, let's say, a capital VGS. And on top of that bias voltage, I've applied a small signal. Okay, you have a voltage that is varying with time like this. Okay. And what is the transconductance of this transistor? It is going to be GM, which is mu Cox W over L into capital VGS minus VT. It's the bias point, right? Minus VT. This is the transconductance. Now, when you look at the small signal behavior of the MOSFET, when I apply a VGS here for an ideal MOSFET, let's ignore channel length modulation and so on. The small signal current that's coming down here is IDS, which is going to be GM times VGS. Okay, I need to find a better tool to write. Write it like this. Okay, so my IDS is going to be GM times VGS. Okay, which in this case is GM times V0, if you think of the amplitude. Okay, and ignore the ignore everything else, right? So this is my current. This is the mod of my IDS. And this is what an ideal transistor is like. But because you also have a displacement current through the gate, okay, you also have a displacement current. You have this C dV by dt current. What is the C? It is Cox into channel width into channel length. That's the total gate capacitance. And what is my gate voltage? What is dV by dt? Since V is V0 sine omega t, dV by dt has got an amplitude of V0 into omega. Okay, only an amplitude. I'm only worried about the amplitude. And what is GM times VO? It is mu Cox W over L into VGS minus VT. Okay, so this is my small signal current through the drain and source, which is what transistor action implies, which is what I want. And this displacement current is an unnecessary component that is getting in. Okay, I'm not really, I don't want any current through my gate, but my gate is a capacitance. That I mean, the gate insulator semiconductor forms a capacitor, and I'm getting this current through the gate. Okay, let's call this as IG. Let's call this as IG. So there is a point, or there is a CC as a frequency instead of this W. Let me use something else for frequency there. I'll say 2 pi f. 2 pi f. Okay. Now, clearly, as the frequency increases, you see this IG is going to keep increasing, whereas my IDS is remaining constant. Constant, quote unquote, because many GM is, of course, frequency dependent. But nevertheless, as F increases, this IGS is increasing. And there'll be a point where this little device that you've built is more a capacitor than anything else. It's not behaving like a transistor because Ig will overwhelm IDS. You're not going to see any IDS. You're only seeing Ig. Okay, at which point it stops being a transistor. So we use a measure for the maximum frequency at which this will still show transistor action. Okay, and that frequency is this transit frequency Ft, where this Ig will be equal to IDS, and any frequency above the transit frequency, my Ig is going to go greater than IDS. Okay, so this is nothing but mu Cox W over L into VGS minus VT. Okay, and therefore here you now have a very clear definition of a transit frequency. Oh, terrible.
Into VO.
Huh?
I think you missed the VO terms.
Into
for
VO, into
IDs.
VO, correct. Sorry. Yeah, into VO. GMVO. Okay, so now you cancel out all common terms. Okay, I'll just keep only this expression now on the board. So you see, you can sort of imagine canceling all the terms that are common, right? So you keep mu, W goes away, Cox goes away. You see, W and Cox and VO goes away. VO is gone, Cox is gone, W is gone, and the L comes down to this side. It becomes L square. Let's say L square, and that's gone. And let's keep the 2 pi, bring it over to the other side. So all this, the VO is gone here. Sorry, the VO is gone, divided by 2 star pi. Okay, so that's my Ft. What's important is it depends on mu by L square. Okay, so if you want to make, so let's say IBM builds a new transistor. Somewhere in the news article, you will find Ft, or they'll say the transit frequency is something. What that means is they have reduced the L to such an extent that this Ft is a very large number. You see, it's very strongly dependent on L. And it's strongly dependent on mobility. So it's dependent on the material property, and it's dependent on your channel length. So particularly when you're talking about scaling, if somebody has gone from, let's say, 1 micron to 1 nanometer, their Ft has significantly improved. It's okay, because there's a 1 by L square curve. It's a very strongly hyperbolic kind of relation, right? So as L decreases, your Ft increases quite significantly. Okay, so that's what Ft is, and that's why it's a useful thumb rule for you to judge your process, the speed aspects of your process improvement. Okay, why does parasitic only at high frequencies? Why does a parasitic gate source capacitance come into play only at high frequencies? For convenience. Okay, so as long as all your other impedances, if the frequency is low enough that all your other impedances are negligible, I mean, are more important compared to the negligible impedances posed by your capacitances, then you ignore these capacitances. We just ignore it. It is always there at any frequency. It is always there. We just ignore it, and we account for it only at high frequencies because particularly at that point, ignoring it will lead to you having wrong calculations, particularly when it comes to the dynamics of amplifiers and so on. Okay, is all this clear so far? How many of you,
Yes,
let me
sir.
make it more interactive, how many of you are actually listening to this and learning something from this? Maybe we can do a thumbs up or something. I don't know what icon we have here. Okay, if all of you can give a thumbs up or something, that will be okay. Either you're not doing it or I don't see any, one of the two. Okay, fine. Yeah, I wish I had a chalkboard and something, it'll be much easier for me to teach. Zoom is a terrible platform for me to teach and write all this. Maybe the next time I'll just go near a board and somebody can record it. Much easier to teach on a board. Why do we have more prominent gate leakage at high frequency? Because of displacement currents, right? So is it advisable to use a digital inverter as an amplifier by choosing the... It's a great question. Okay. Can you use a digital inverter as an amplifier? Okay. Technically, a digital inverter is an amplifier. It's a common source amplifier. So if you think about it, you have, let's say, a PMOS, then NMOS, sorry for the terrible drawing. Okay. And if I were to draw, if I want to use VN and V out, first let's think about the digital world, right? So what do? You have a V out versus V in curve that looks like this. Okay. The only reason why this will have a slope, let me make it more interesting. Okay, let me make it a little bit more interesting, the answer to this question. So here's your digital inverter. Okay, so let us say I ask you to tell me that this is Vn. Sorry about that. And this is V out. And I ask you to tell me how is V out related to Vn. You'll see that if I have to calculate it, sorry about this. Yeah. I have to calculate it. My mu Cox W over L into Vn minus Vt, the whole square, Vtp, the whole square is the current by 2 is the current through the PMOS.
Sir, I'm unable to see the screen.
You are unable to see the screen?
Writing's not visible, sir.
Oh.
The remaining content so far is visible, but
Is
like
it?
from the inverter question, it's not visible.
It's not visible. Can you see it now? Is it just a lag or something?
No, not.
Okay, I'll just explain it. Okay.
Oh.
You cannot hear me, right? Yeah.
I can hear, yes.
Okay. So, so what happens is, if you write out the KCL for the inverter, you'll find that the V out term disappears, right? The V out is poorly defined. V out will not appear in the KCL for this inverter at the output. Okay, so but an inverter can be used as an amplifier. If you draw a V in versus V out curve, you'll find that there's a very sharp steep, right? That's how you look at it in digital circuits. And the only reason why that vertical steep will have any finite slope and not an infinite one is because of channel length modulation. So unless you have channel length modulation, that slope will be extremely sharp. It will go from PMOS being on all the way to NMOS being on almost immediately, right? If you do not have channel length modulation. Now, where do you use it as an amplifier? You use it as an amplifier when both these transistors are in saturation. Okay, that is in the region of that slope. So if you were to look at the dV out by dV in curve, the dV out by dV in curve, you'll find that the dV out by dV in is got the highest value at that slope during that transition, right? That's where you use it as an amplifier, common source amplifier. So yes, it is a common source amplifier with both the NMOS being the driver and the PMOS being its load, and the PMOS being a driver and the NMOS being its load, because the input is applied to both. Okay, and you can actually use superposition if you wish to calculate the gain. The gain will be something like GMP plus GMN into, if you have channel length modulation, RON parallel ROP. And if you don't have channel length modulation, the gain is going to be infinite. Okay, so that's, yeah, so you do have this being this thing. You can use it as an amplifier. I don't know if that's clear. Much easier to write it out and show you this, but could you follow it?
Yes, sir, I could.
Okay, could you suggest some good journals, professors? Okay, you can send me an email. There are so many good people working in this. It's just too much to talk about here. Papers and journals and so on. I can strongly advise. Journals, two strong journals are IEEE electron device letters, transaction electron devices, or IEEE Journal of Solid State Circuits, Journal of Transactions and Circuits, I mean IEEE Transactions in Circuits and Systems. All these are some of the very good journals. On the more physics side, Applied Physics Letters, Physical Review B, Physical Review Applied. These are all some of the journals, but just too many textbooks and too many good journals. If you send me an email, I can respond to that more effectively.
Okay, sir.
Okay.
So also
Yeah.
please have a look at the 13th question.
13. Okay. Oh, sorry, I missed that. What is the difference between gate overlap capacitance and gate source capacitance? Gate overlap is between the source and the channel region, right? So I'm sorry, between the gate and the channel, gate and the source near the channel region. Okay, let me draw it. Let's draw it. It's much easier to explain by drawing. Can you see this drawing, which I do here? Can you see this? The source.
Yes, sir, I can see.
This you can see. Okay. Okay, there is an insulator here, and there is a gate here. So this is your gate overlap capacitance. Okay. Now, gate to source capacitance is a bit more tricky. Depends on what region of operation you are. If you are in the off state, then if you are in the off state, then the gate overlap capacitance, there is some on the source side, there is some on the drain side. Okay. But let's talk about two important regions. One is in linear mode operation, one is in saturation mode operation. In linear mode operation, you have a channel. And the gate to source capacitance will include the gate overlap capacitance plus the channel influence, half of it. So it will be Cox into WL by 2. So half of this channel capacitance will also fall under CGS. But if you're in saturation operation, you will have a gate overlap capacitance. Okay. So there'll be a C overlap capacitance. And your CGS, you can actually prove that it's about 2/3 of what it was in the linear mode operation. It'll be 2/3 of Cox into WL. So this is basically this contributes differently when you're in linear mode operation and in saturation mode operation. Okay, so your CGS depends on which mode of operation you are in. Your C overlap is always constant. It's a geometrical overlap parameter. Okay. So, and since all the carriers are coming in from the source, that is your CGS. It belongs to CGS. Okay, is that clear? That's your 13th.
Yes, sir. So basically, the gate source capacitance is actually a series combination of the overlap capacitance and the channel capacitance.
No, not series combination. You can put these in. It's like this. It's more like parallel. So you will have overlap capacitance between gate and drain, and you will have CGS, which will be a combination of all these, which will include the effect of the channel, which will also have, if you wish, you can draw it like this. You have a gate to source capacitor like this, and if your source is at ground, this is also at ground. So geometrically, this capacitor lies like this. This is how you want to actually show the overlap capacitances. This is the overlap with the source. This is overlap with the drain. And only when these two potential are the same, or but divided by 2, and all this together, you can sort of group it together as your effective capacitance seen by gate and source. Okay.
Okay, sir.
Okay, so what would be the effect of thickness on the tunneling? It's okay, yeah. So this, I think we answered this right at the beginning. So we have a question by Dariksham. I think you're talking about the barrier width, right? So the barrier width, yeah, when you increase the doping in a metal semiconductor junction, as the barrier width decreases, your tunneling will increase. So you will have, the probability of you having carriers on the other side increases. Okay, so increasing the doping will reduce the barrier width. I mean, this will reduce this, will make this band bending much steeper, reducing the barrier width, and therefore the tunneling probability increase. I mean, the probability of finding carriers increases. The tunneling becomes much stronger. Okay, so that's what happens. Okay, so there are okay, yeah. Again, Kamaljeet has a question on gate preparation, suggesting good books. Yes, send me a email. I will respond with. There are many good textbooks. Just so many to count. But so just send me an email and I will suggest some excellent textbooks. You can even view courses by other faculty in other universities. So much you all have access to YouTube and so many online resources. There's no shortage of any knowledge. There's plenty out there and plenty of good stuff out there. So please send me an email and whatever resources I know, I will point you to it. Okay, but I'm sure there's plenty of stuff even beyond what I can suggest. Okay, fine. I don't see any other questions here. So if that is all, how did all of you enjoy this course? Did you all learn anything from it? What's it like? If I allow all of you to speak or give a thumbs up or type in chat, any suggestions for improving this course and so on? Yeah, can all of you hear me? Or all of you are very shy. I don't know which side is.
Yes, sir, you are audible, sir.
Yeah. So how did you all like the course? Was it helpful? Was good? Any suggestions to improve the course? Or should I just keep it as it is? Okay, Sandeep is all fine. He gives a 2 thumbs up, I think. But what about the others? Okay, if you all have feedback, looks like I have a very shy audience here. Second week assignment, one answer is wrong. Okay, let me take a look at it. I need to talk to, I don't know if my TAs are here. I don't know which assignment that is. I will take a look. I need to speak to the, I will have a chat with my TAs. I'm quite experienced, so I don't know whether they made a mistake or what it is. I will take a look at it. Okay, so yeah, assignments, I actually don't handle it. We would like a deeper coverage of certain solid state topics. Okay, that's a very hard thing to do, right? See, I'm trying to balance out, I'm given something like 30 hours to conduct this course. So it's hard for me to cover everything and go in depth, but let me see if I can add more content, right? Even beyond this course, if I have some content, I will try to share it with you. In fact, when I teach this course here to grad students, we go a little deeper in all these topics, right? There's a lot more material. So let me see how I can get that across to you. Monday problem sessions are not happening. Okay, that's blame relies squarely with my TAs. I will check as to what's going on. Okay, Prasad, if you can send me an email, send me a formal complaint on this. I will forward it to both. And in fact, you can send it to NPTEL and they will check with my TAs as to see why this is not happening. Okay. Okay, if you like more one-to-one interaction, I like to do this. Yeah, of course, I will love to. But the only thing is, I'm much more comfortable on a blackboard. And maybe if anybody from NPTEL is listening, the next time we run this course, we can have more interactive sessions. But I will stand in front of a blackboard and explain. Writing on this whiteboard is really hard for me. I'm not enjoying this at all. writing on this whiteboard. I myself cannot read what I've written. I'll go back to it. So if I'm standing in front of a blackboard, it's much more fluent. I can be much more fluent. It can be done. We can handle a lot more questions. Thanks a lot, Kamalji. Thank you very much. Fine. Okay, amazing. I'm very happy that all of you are learning from this. Yeah, any other questions you have, any comments, feedback, etc., feel free to email me, but much more effective if you can email the NPTEL team. Okay. Yeah. Could you brief us on device characterization versus device modeling? Device characterization versus device modeling. So device characterization is the experiments that you do. So you build a device and you go measure the IV characteristics, or you measure the CV characteristics, or you do whatever tests you have to do. Need not be just limited to these characteristics. You have material characterization, look at the surface morphology, maybe using an SEM, AFM, etc. Then you have electrical characterization. Then you look at the electrical Then you have other material techniques. You can do EDAX, or do other stuff to find out what kind of bonds you have or what kind of species you have on your material. So there are various kinds of characterization. And after you do all that, you take all that results and you have experimental data in front of you. And then you have built the device, so you know the physics of the device. So you've got your theoretical models. Models are basically working out with maybe a paper and pen, or the more modern day is using a computer, but I still strongly recommend paper and pen, because to a broad extent, you should be able to put down everything in paper and pen using very simple ideas, simple models. And once you have it on paper, then you look at experiments and see whether your theory matches your experiments. If it doesn't match your experiments, then your theory is not complete. And then you might want to go and see why it is not complete. What are those signatures that you see repeatedly on your experiments that your theory doesn't explain? Right? Some of it might be just experimental errors or experimental artifacts, but you measure enough devices, get a statistics, and you will see some very consistent features. And if your theory is not explaining it, that means your theory is not complete. So experimental characterization goes hand in hand with modeling, and these two work together to form a much better theory and a much better understanding of the device. Okay, that's basically what device physicists do. Okay, so that's the answer. Okay. Okay, so if there is no other point of discussion, is it okay if we end this meeting?
Yes, sir.
Okay. Okay, I wish all students the very best. Where can I? No. You send a message. NPTEL is the best place. You please send a message to them, because if you send a message to me, I might lose it in case I'm not expecting it. But I will give you my address. That's my email address. You can send it there. And I wish all of you all the best. Whatever your career choices are, career paths are, I wish all of you achieve your goals, your dreams. Just work very hard. Try to always keep in mind the very basics, the fundamentals. Never always try to strengthen your fundamentals. Try to strengthen your understanding. You don't have to go to the cutting edge of technology. Whatever you have, as much as you make your foundations very strong, the other things will easily follow. Keep your physics and math very strong, right, all the time. And when I say physics, I don't mean only semiconductor physics. Make your physics very broad. High school physics, right, should be very strong. So that's my only suggestion to all of you. Okay, very good. Thanks. It's a pleasure teaching you. I really like teaching this course. I also teach another course, Analog Integrated Circuits at IISc, which is also quite popular here. At some point when I have time, I will make it an NPTEL course. Okay, fine, perfect. Great. I wish all of you the best. Nice to hear so many nice words. Thank you so much. Okay, and I will close this session. Thank you. Thank you, everyone.
Okay, sir. I'll make end for everyone. Thank you, sir.